Avoiding shading from obstacles in photovoltaic systems is important. Shading can significantly impact the overall performance of photovoltaic panels. Even a small amount of shade can reduce their output by up to 80%. Therefore, a thorough assessment of the area and careful selection of the installation site are required in order to ensure the optimal performance of the system. Unwanted shading can occur from a number of sources, such as trees with spreading branches or thick foliage, bushes that may grow taller over time, buildings that are nearby or newly constructed, adjacent PV panels that are positioned closely together, poles like utility or streetlight poles, and other similar objects that can block sunlight. A properly selected area. So, a properly selected installation area should remain unshaded during the solar window, within a specific time frame, on any day of the year. So how can we carry out this evaluation? How can we evaluate and avoid shading from nearby obstacles or even from one panel to another? And that's what we'll be looking at in this video. So the evaluation of an area can be easily carried out with the help of the region's solar map. What is the solar map? The accurate representation of the sun's path throughout the year, as observed from Earth, is referred to as the solar map. This map determines the sun's position for any hour of the day for every month, at the specific geographical latitude of the location. Greece, from the south of Crete to its northern borders, is located between 32 degrees and 42 degrees north latitude. The bottom horizontal line, the abscissa, determines the sun's azimuth in relation to the south, which is located at the center. The vertical line, the ordinate, determines the sun's altitude angle for all hours of the day and for all of the months. So, if we want to calculate or determine the sun's angles for a specific month and for a specific time of day at a location with a specific northern latitude, we follow the procedure below. We select the solar map that corresponds to the specific latitude, phi. Next, we find the sun's path for the specific month of interest, so we can find the sun's position, and the hour curve for the time we also want to see where the sun is located. From the intersection point of the sun's path and the hour curve, we draw a vertical line down to the abscissa. This gives us the sun's azimuth in degrees. And then, from that same intersection point, we draw a horizontal line perpendicular to the ordinate. This gives us the sun's altitude angle, also in degrees. Therefore, with this particular method, we can accurately determine the sun's position during the solar window, and for any month that we are interested in for the month of interest. And so we can estimate the direction of the sun's rays in relation to our photovoltaic park. So in this way, we can investigate the sunlight conditions of our photovoltaic park. So by knowing the sun's position, the sun's altitude angle, and its azimuth relative to the south, we can place the sun at the correct point. For the hours within the solar window, carefully draw a line that corresponds to the direction of the sun's rays, and observe how the shadow of each obstacle is cast. If you want to be the engineer who provides solutions and not just products, then specialization is the only way forward. If you're interested in learning how to do it the right way and offer solutions for photovoltaic systems step by step with real tools and simulations, then take a look at our free lessons. The link is below this video.
So subscribe and comment below. Tell us what you would like to learn next about engineering, buildings and energy systems. Personally, me and my team, we read every message, and your feedback shapes our next videos.